Check, check, check.
Okay.
Check, check, check. Check.
Okay, shall we resume?
Check.
Okay, so maybe let's continue. Okay, so what did we do before the break? So we looked at logistic regression, and we also discussed how to do gradient descent for logistic regression, right? And there was this question about like whether there is a closed form solution for logistic regression, like because the gradient looks very similar to linear regression, right? Like, so we're going to talk about that now. So now, first of all, like when you consider linear regression, okay, so we have closed form solution. Right? Now, can somebody tell me what, don't say my pen is not writing. Just give me 1 second. What happened to my pen? It should work. My notepad is updating. But still it is not writing. Okay, just give me 1 second. I need to close this, open it again. Still my pencil is not writing. As a backup, does anyone have a old generation? Okay, it's writing. Maybe I should start bringing a backup pencil. Okay. Now, in the case of linear regression, there is a closed form solution. So can someone tell me what their closed form solution was? Someone who has not answered so far. And this is probably a hard question. Sorry, what is that?
X transpose X square, X transpose Y.
Well, it's almost correct. Well, as I mentioned before, I don't expect you to remember like closed form solutions often, but this is one thing which you have seen many times. Like by now, you should remember this by heart. Like so it was X transpose X inverse X transpose Y, right? Okay. Now we also discussed why we have closed form solution for linear regression. Like why? Because in this case, your error function was a quadratic function of parameters. So when you have a quadratic function, like you can differentiate it, set it to 0, you'll get closed form solution, right? However, in the case of logistic regression, okay, so your error function is actually a non-linear function of x, and this non-linear function is not quadratic. there's a sigmoid nonlinearity, right? Like, so you have sigma of W transpose X, which makes things more than quadratic, okay? Now, it is not a quadratic function, okay? However, this error function is still a convex function. I assume you have done the reading about convex functions, which was several weeks back, right? So even if not, we have discussed about convex functions a little bit in the class. Like, we know that for convex functions, there is a unique minimum, right? Like, there is only one minimum, so global minimum is equal to local minimum, right? So we still have one solution for logistic regression, like not many solutions, okay? Now, when you have convex problems, okay, there are actually more efficient methods available for like faster convergence than gradient descent. Okay, so we are going to look at one such method today, which is the idea of Newton Raphson method. Okay, I'm just curious, how many of you have done a numerical methods course? Some of you, okay. I highly recommend people who have not done a numerical methods course to do one. Like, it's very useful. Like, you'll see a lot of practical applications of numerical methods. Like, so now if you have done a numerical methods course, probably you would have seen Newton Raphson method for computing derivatives, right? So we are going to redo it today, like for people who have not seen this before. Okay. Now, Newton Raphson method is actually, it's also an iterative method like gradient descent. Okay, so it's an iterative method. Okay. Now, in the case of Newton Raphson, like, we are going to use a local quadratic approximation to the error function. Okay, so we have an error function which is not quadratic, right? But what I'm going to do is I'm going to assume that the error function is locally quadratic, which means I can find the closed form solution for that local approximation. From there, I again make another quadratic assumption and continue. Okay. Now, as you can imagine, this takes much bigger jumps than doing naive gradient descent, right? Like, so, like, we will see geometric interpretations soon, but for now, let's write how the approximation looks mathematically. Okay, so we are going to take a local quadratic approximation to error function. Okay, so specifically, we are going to use second order Taylor series expansion for E of W. Okay, so I am going to take E of W. I'm going to approximate this at some point W0. We're using second order Taylor approximation. Okay, so now this is going to be E of W0 plus W minus W0 transpose of gradient respect to W plus 1 over 2 W minus W0 transpose H W minus W0. Okay, where H is basically the Hessian of E with evaluated at W0. Okay, so Hessian is the double differentiation, like, so it's like dou square E by dou W. Okay, is that clear? Okay, now if I make this assumption, right? Okay, let me take this to the next page. Copy. Okay, I'm going to make this assumption approximation for E of W. So now, instead of differentiating this E of W and setting it to 0, I can actually differentiate the right-hand side and set it to 0, right? So I'm going to differentiate this, okay? Now, E of W0 is evaluated at a point, okay? So the gradient is 0, okay? Plus, for the second term, it's going to be just E of W, okay? Plus, so why is it, do you understand why I put just the gradient here? Like, because it is W times del E. So when you differentiate W times del E, we just get del E. Now W0 is a number, it's not a parameter, it's a single scalar, so the gradient is 0. Now, plus you have x square by 2. So when you differentiate, you get 2x, 2 cancels, right? So you just get W minus W0 transpose multiplied by the Hessian is equal to 0. Is that clear? I have differentiated it and set it to 0. Now, W minus W0 transpose H is equal to minus gradient. Okay. W minus W0 transpose is equal to minus H inverse of the gradient. Right? Now, W is equal to W0 minus H inverse of the gradient. Okay. Now, I can write an update equation based on this. My new W is going to be equal to old W minus H inverse of value of W. Is that clear? So this is Newton Raphson. Now to compare this with plain old gradient descent, can someone tell me what would be the updated equation for gradient descent? So W new is equal to W old minus alpha times gradient. Right? So this is gradient descent. Right? In the case of gradient descent, you had an extra hyperparameter, which is alpha, which is the step size, which created all the troubles, right? Like, so you have to take smaller alpha, but not too small, right? Like, so you have to tune this alpha. However, as you can see, Newton Raphson doesn't have a hyperparameter alpha. It just is computing Hessian, which is basically dou E square by dou W. It's a matrix. Okay. Now alpha is a scalar. However, H is a matrix. Okay. Now this matrix, if you have n parameters, it has n square entries. Okay. So you have a matrix Hessian multiplied by the gradient. Even though it doesn't have a separate hyperparameter, which might look tempting that you should always use Newton Raphson instead of gradient descent. Like, you should remember that this is a computationally very intensive algorithm when compared to gradient descent. Okay, because in Newton Raphson, for each time step you have to take H inverse. Now this H is a huge matrix, and matrix inversion is order n cube. Okay, so now it's going to be extremely slow if you have many parameters. If you have small number of parameters, then you can afford to compute Hessian. Is that clear? Yeah.
Can you calculate the Hessian inverse once or at each step?
At each step. So, okay. Now, the first observation is, if you have a quadratic error function, okay, then this second order Taylor series approximation that we have is actually not an approximation. It's going to be exactly equal. It's going to be exactly equal for quadratic error function, right? Because quadratic error functions don't have power 3. So the rest of the terms will become 0 in Taylor series. So it is actually exactly same, which means if you apply Newton Raphson for a quadratic error function, there is no approximation involved. So you should get your answer in just one iteration. Okay, so we're going to verify that before that question.
I don't know if it's the term that's different in English, but what is the Hessian?
Oh, it's the second order derivative.
Do you know the name in French? No?
Is there a French name for Hessian? So what is it called? Just Hessian? Okay. Okay, so now let us verify that. Okay, so let us verify that this is not an approximation and direct answer for linear regression. Okay. Now in the case of linear regression, our error function is given by 1 over 2 summation n is equal to 1 to capital N W transpose phi of x of n. In this case, I'm using a linear regression with basis function. Okay, minus t of n the whole square, right? Now when I compute the gradient, it's going to be summation over n is equal to 1 to capital N, W transpose phi of, I'm just going to use a shorthand notation, phi of n, okay, minus t of n multiplied by phi of n, right? I've just differentiated it once. Now I can actually write this in matrix or vector notation. So this is nothing but phi transpose phi w minus phi transpose t. Okay, so there is a summation term, like I have just converted into a vector operation. Why? Because I'm going to do another differentiation now. Okay, so now this is the gradient. Now what is the Hessian here? The Hessian is given by the double derivative, which means I just need to differentiate this one more time. You differentiate this one more time with respect to w, what do you get? What do you get if you differentiate del E with respect to w? Sorry? Yeah, just phi transpose phi, right? So you just get phi transpose phi, right? Now let us actually write the Newton Raphson update for linear regression. So it's going to be W new is equal to W old, okay, minus the Hessian inverse. So phi transpose phi inverse, okay, multiplied by the gradient. So the gradient is given by phi transpose phi W minus phi transpose T, where this W is the old W, right? Now, W new is equal to W old minus, I multiply this inverse, I bring the inverse inside, so this becomes minus W old plus phi transpose phi inverse phi transpose T. Okay, now this cancels, so my W new is nothing but phi transpose phi inverse phi transpose T, which is basically the standard least square solutions, but we have derived it using Newton Raphson. So when you have a quadratic error function, Newton Raphson gives you one-step answer, which is more efficient than gradient descent, right? Like the gradient descent is going to give you, but it's going to take, you might have seen this in the assignment, like it's going to take thousands of iterations, like probably, like sometimes like lots of upgrades, right? Like so Newton Raphson is efficient, but very computationally expensive. Is that clear? Any questions? Oh, okay. Okay, yeah, I always make this mistake. Thank you. Okay, I know sometimes I confuse you by dropping transposes or adding transposes. I'm really sorry, but you should try to be robust to the transposes really. Like for most of these equations, the good thing is there's only one way to implement it. Okay, so if I put transpose wrong, you will not get the correct shape out of it. So you can figure out whether there's a transpose or not when you're implementing it. Like you don't need to pay too much attention to a transpose, even though it's a good thing to do. Okay, so now let's actually look at the geometrical perspective of gradient descent and Newton Raphson. Okay, now this is to talk about intuitions. So gradient descent versus Newton Raphson. Okay, geometric view. Unfortunately, the screen disappeared again. Let's just wait for a few seconds. Come on. I think the I think the camera is giving us forced breaks. Okay, it's clear. Okay, so we're going to look at gradient descent of Newton Raphson, and see how they behave in terms of geometrical view of the loss function. Okay, now let us just consider like a convex function. Okay, to make things simple. So I have a function like this. Okay, to make it similar, I'm going to copy this twice, like once for gradient descent and one for Newton Raphson. Okay, now in the case of gradient descent, we randomly start at some point and we compute the gradient and we go in the opposite direction of the gradient, right? So which points us towards the minimum. But then we don't know how far to go, so we take an alpha step, right? So you take a tiny step, you reach here, you take another tiny step, you reach here, you take another tiny step, and so on, right? So this is how gradient descent behaves, right? Now, depending on how big or small is your alpha, you're going to take many, many steps to reach the minimum, right? However, Newton Raphson is efficient than gradient descent in the sense, let's say you are at this particular point, okay? It first makes a local quadratic assumption, which means it constructs a quadratic function like this here, okay? Now, for this quadratic function, you can take an efficient one step to solve the problem, and you reach here, okay? You project that to the loss function, and you reach here. So now you see the fundamental difference, right? So Newton Raphson can actually take much larger step because of this approximation that it is making. It makes some approximation, it goes to the minimum of that approximation, and the corresponding place in the loss function is where you get. Now you make another quadratic assumption here, approximation here, okay? And you find the minimum of that efficiently closed form. You're here, okay? And another one, like you're here, or another one, like you reach here. Okay. Now, from the loss surface perspective, you can see that Newton Raphson is actually moving much faster. Is that clear? Now I'm going to show you a little bit non-trivial geometric view. Okay, so let me know if you don't get it. So we are going to look at, so this is function f, right? So we're going to look at how these algorithms behave in f dash space, okay? So in the case of f dash, okay, you have f dash is equal to 0. Let's say this is f dash is equal to 0, which is your minimum, okay? Now, in the case of gradient descent, your f dash reduces, and at some point it becomes 0, okay? Now, in the case of gradient descent, you take one step at a time here, and you eventually reach f dash is equal to 0, okay? Now, this step is again based on your alpha, okay? Now, if you think about how Newton Raphson behaves, right? So in the case of Newton Raphson, okay, at any point you are, okay, so Newton Raphson actually finds the tangent, okay, and see where this tangent cuts f dash is equal to 0, and that is my second space, okay. Again, you find the tangent wherever it cuts. This is your next step, okay. So Newton Raphson is efficient in the sense it is actually using the local curvature information. Like it's a second order method actually, okay. So it uses the local curvature information while gradient descent is agnostic to the local curvatures. Like so, Newton Raphson efficiently exploits the curvatures. Like if you have a good curvature, you can go faster, like by exploiting the curvature. On the other hand, gradient descent doesn't do that. Is that clear? Any questions? Okay, so now that I have introduced, yeah.
When you say local, I am trying to see it in a practical way. We don't have to define any neighborhood by ourselves.
You don't want to? Can you please repeat the last part?
Yeah, we don't have to decide any neighborhood by ourselves. When you say local, we just have to compute the Hessian matrix.
Oh, yeah. Oh, so, but I'm giving geometric perspective, right? So it is not about like reconstructing these things. Like, so when you compute, you're just computing the Hessian. So I'm only trying to show you what it means to use Hessian. Like, how is it efficient? Okay, so now that I have introduced Newton Raphson, so now let's actually go back to logistic regression. Now we are going to do Newton Raphson for logistic regression. Okay, we have already done Newton Raphson for linear regression, which was a small exercise. Now Newton Raphson for logistic regression. Okay, now it's not that complicated. Okay, so our error function is minus ln p of t given w, right? Now this is basically minus summation over n is equal to 1 to capital N, t of n ln y of n minus 1 minus t of n ln 1 minus y of n, right? Now, oh, by the way, I think I forgot to put it in the notes, but this negative log likelihood in binary case, right? So this is also called as binary cross entropy. So if you're using packages which has a binary cross entropy loss, it's same as NLL. Okay. Okay. So now I'm going to make this. Okay. So this, like we know this is E of W, and we have also computed the gradient, right? So del E of W is given by summation n is equal to 1 to capital N, y of n minus t of n multiplied by x of n, right? Now I want to differentiate this again, so I'm going to make it a vector notation first. So this is nothing but x transpose y minus t. Okay. So now I can compute my Hessian. My Hessian is del E of W. Okay, which is basically like if you look at the first part, summation over n is equal to 1 to capital N. Okay. So what would be the differentiation of this with respect to W? Anybody? So I think I wrote it directly in the notes, but it's not that complicated. So you are looking for differentiation with respect to W, right? So you will only consider this part. There are two terms here, yn xn and tn xn. So tn xn doesn't have W, so that differentiation is 0. So it's only yn xn. Now y is basically a sigmoid function, right? Like it's a sigma of W transpose x. So when you differentiate that, you get sigma into 1 minus sigma. Then you differentiate W transpose x, you get x, right? So I'm going to write it directly. It's basically y of n into 1 minus y of n multiplied by x of n. There is also another x of n already standing outside, so I'll add that as well. Is that clear? Well, if I have to do the derivations, probably 3-4 steps. Like I'm putting it directly because we have done this routine again and again. Now, I can actually write this in a different form. So I'm going to write this as x transpose Rx, okay, where R is a n cross n diagonal matrix, okay, where Rn is equal to y of n into 1 minus y of n. Is that clear? Okay, so now you can see that this Hessian, right, is actually a function of R, right? In the case of linear regression, it was just X transpose X. But in the case of logistic regression, it is X transpose Rx. Now, what is this R? This R is a function of Y. Now, what is this Y? Y is a function of W, right? Or in other words, my Hessian computation is dependent on W. So when I use the old W and compute the Hessian, I'm going to get a new W. I have to repeat this process again and again until I converge. Is that clear? In some sense, my Hessian is computed by this weighted term, where the weight is coming from, the weighting matrix W is coming from W itself, right? Is that clear? Okay. So now, with this formulation of Hessian, right? Like, so now I can actually show you that logistic regression is actually a convex thing, okay? So now we know that Y of n is between 0 to 1, right? Because it is a logistic sigmoid. Sigmoid value is between 0 to 1. So this is based on the fact that it's the property of sigmoid, right? Now this means that U transpose H of U is greater than 0 for arbitrary vector U. Okay, I'm not going to prove it. It's linear algebra. Now, this is the definition for positive definite matrices. So H is positive definite. Okay, when H is positive definite, then that means that the error function is a convex function of W. So it is one of the conditions for convexity that your Hessian is positive definite. Okay, now this further implies that the error function has unique minimum. Okay, or in other words, you start with any W, you apply Newton Raphson again and again, you will always converge to the same solution. Is that clear? Okay, now we have only computed the Hessian, right? Like we haven't computed the update rule for Newton Raphson. So Newton Raphson update formula. So W new is equal to W old minus the Hessian. My Hessian is given by X transpose R X inverse multiplied by the gradient, which is given by X transpose Y minus T. That's right. So now I'm going to do a little bit of restructuring here. Okay, so I'm going to take X transpose R X inverse out. Okay, there is no such term in the first part, so I have to add it. Okay, and minus X transpose Y minus T. Is it clear? Equal to X transpose R X inverse. I'm going to call this whole thing as X transpose R Z. Okay, where Z is an n-dimensional vector. Okay, which is basically the rest of the terms X W old minus R inverse Y minus T. Is it clear? So I have just added, like I've just restructured things here so that, but it is exactly the same equation. Okay. So the reason why I did this is because now, if you look at this equation, right? So this equation. So this equation looks exactly like least square, but with extra weighting term. The solution for least square was X transpose X inverse X transpose Y. Now I'm weighting them by R matrix, right? Now this R is a constant, but it depends on W, right? This R is going to keep changing, right? So, or in other words, you can view this algorithm as reweighted least square, okay? And since you are doing this iteratively, right? So, like often in literature, we call this algorithm as iterative reweighted least squares. IRs. Okay, so iterative reweighted least squares is nothing but applying Newton Raphson method for logistic regression. Is that clear? Any questions about Newton Raphson? Yeah.
I'm not clear why you actually compute R if R is dependent on
R is dependent on W, right?
well, the formula
Sorry, what?
given earlier is only dependent on Y.
Y. But what is Y?
Oh, okay, yeah.
Y is sigma of W transpose X. So your R gets R gets stale once you do the update, right? So you have to continue until like W doesn't change. Okay, any other questions? Questions in chat? Okay, so well, that concludes our discussion on logistic regression. Okay, but I want to make a quick note about maximum likelihood itself. Okay, before we continue. Okay, so note. So maximum likelihood can actually exhibit severe overfitting for simple problems. Okay, when you have a linearly separable problem, which means you can fit a straight line to divide the data set perfectly, okay, then logistic regression is going to have some troubles. Okay, let me explain you why. So okay, sorry, it's not logistic regression. Maximum likelihood is going to have some trouble. Okay, let me explain you why. So now let's take a simple problem. I have a bunch of cross and I have a bunch of circles. Okay, now, so the maximum likelihood solution would happen when you have a plane which separates these two data points, right? Now this plane equation is given by sigma is equal to 0.5, right? Sigma of W transpose X, let me write it fully. So sigma of W transpose X is equal to 0.5, right? Now, this is actually equivalent to W transpose X is equal to 0. Okay. Now this W transpose is equal to X is equal to 0. It separates the two classes, right? Now, let's say this is that line. So once I find this line, right, I can continue to update my W and keep on increasing the value of W. Because the direction is not determined by the magnitude of W, right? So the W, like what would normally happen when you are using maximum likelihood solution of logistic regression with a data like this is your W is going to just keep on increasing after you find the solution, okay? Like I can give you an example, like let's say you initially start with some classifier in some random initialization, okay? You will slowly do gradient descent and this improves. The moment you find a line which separates the two, you have zero error, okay? But you will still receive gradients and like you are just going to keep on increasing the value of W and you will run out of numerical precision at some point and your code is going to crash, okay? If you want, you can actually verify this by implementing gradient descent for logistic regression. Like you will see that it crashes for simple problems like this, okay? Now, this is not the question of amount of data set. This overfitting is not for the data set, okay? Even if you have millions of data points in both the sides, okay? As long as the problem is linearly separable, you're going to have this issue. Okay? You have to be careful about applying this model with simple data sets. Now, in that case, how would you solve this issue? Sorry, what? You can have a stopping condition, like, so if your validation loss is not improving after some point, probably stop any other method. Anything else? No, we are talking about how to fix this issue with logistic regression. Any answers from chat? Sorry? It's not the question of hyperparameter. Whatever hyperparameter you use, you're going to have this issue. Yeah. You can penalize the weights, right? Like you can have regularization term, which says that, oh, you cannot maximize W after some point. Or, sorry? Sorry, what? Wait, yeah. So you can do regularization. Or we can actually do something better than maximum likelihood, okay? So we can also do, there are other estimators available, like other than maximum likelihood. Probably we will not talk about this right now, but we are going to look at alternatives for maximum likelihood towards the end of the course, okay? So I think this concludes our discussion on discriminative models and like maximum likelihood and stuff, okay? So now to give you a very quick recap, right? So we have seen generative models. Like I'm going back to the recap. Like the example was GDA, naive Bayes, right? And you have seen discriminative models. Example is logistic regression. And we have also seen discriminant based models, which is least squares, right? So now let's actually take some time to understand the advantages and disadvantages and like when to choose which model, right? Like, so it looks like a laundry list of algorithms, right? Like, so which algorithm should I pick given a problem, right? So first let's start with, we're going to talk about the merits and demerits of all these three approaches, okay? So first let's start with generative model. Okay, now as you can already see, generative models are the most demanding class of algorithms out of all the three that we have seen so far, right? Like because it requires estimating joint distribution, which could be very expensive or just not possible with smaller amount of data if your number of features is large, right? So now when you have high dimensional X, okay, when you have high dimensional input, then generative models require lots and lots of data to estimate the mean and variance effectively. Okay, now that is the demerit of generative model. But generative models actually have a lot of advantages. Okay, so the first advantage is, well, first of all, like it's much more powerful, right? Like, so once you have this distribution, then you can ask any question that you want about the data. You can answer it efficiently, right? There's also an additional advantage, which is basically with the generative model, you can compute, given a new data point, okay, you can compute P of X, which you can never compute with discriminative models, right? Like because discriminative models just do P of Y given X. With generative models, you can compute P of X, okay, which is basically summation over K, P of X given Ck, P of Ck. Okay, now this can be used to detect outliers in the data. Okay, let's say I give you a new data point. Now you can compute P of X with your model. If P of X is too low, then it is an outlier, like it doesn't belong to the data, right? So now you can use this for outlier detection. Okay, so can someone tell me why would we be interested in doing outlier detections?
Why are you interested in outlier?
Sorry?
What's the question?
So when would you be interested in outliers?
When you want to find the class of the, when our interest is to find the small classes. You have a big class and a small class. You want to separate that small class, the minority class.
Okay. For minority classes, any other?
In the fraud detection,
Sorry.
fraud detection,
Okay. Yeah. So I think they're both similar answers. Like so, fraud detection, like where, like you have a bunch of normal transactions, like which are majority. Sometimes you have these outliers. Like so, sometimes there is this transaction, like which doesn't make sense. Let's say you're using a credit card. You might have seen this already. Like so, whenever you want to make a huge purchase, let's say your average purchase is like less than $100, right? Like you try to make like a $2,000 flight ticket. You would get a notification in your text message saying, hey, something unusual is happening with your account. Like, so can you verify if this is you, right? So that is an outlier detection. Now, you can also use outlier detection as a pre-processing for like your classification problem or regression problem. Like, so you can do outlier detection in the data set and then eliminate all these outliers and then learn a model for regression or classification. Okay, there are many other advantages of doing outlier detection, and you can do that if you have a generative model in hand. Is that clear? Okay. Now let's try to compare generative models and discriminative models. Okay. So generative models versus discriminative models. Okay. Now, if our goal is just to make classification, like if I say my objective is just to get better prediction performance, then probably you are better with just estimating P of y given x. Okay. Why? So here is an example. So in the left side, you see the class conditional densities, P of x given C1 and P of x given C2. Now you see that the first class looks a little bit more complicated, right? It has two modes. It looks complex. However, if your goal is just P of C1 given x and P of C2 given x, right? Estimating the class, then I don't care about the structure here. Like I only care about where to separate, right? Now that is what the right-hand side shows you. Like the decision boundary is where you have the minimum error, and this decision boundary doesn't need to know that there are 2 modes or 5 modes or 10 modes in the first class. Okay, so whenever, or in other words, P of x given C1 has no effect on the posterior probability. So as in the mode of, like, okay, so maybe I'll correct myself. So this left mode, right? This left mode was nothing special when it comes to P of C1 given x, right? So all that matters is there is a lot of class 1 here. It doesn't matter whether there is 2 modes for class 1 or 3 modes for class 1. If you do graph generative models, then you will spend so much time in estimating P of x given C1 accurately. However, it is not helping you with your final goal, which is the classification. Is that clear? So in such situations, like you are just better with discriminative models. Now let's talk about discriminative versus discriminant based models. Discriminative versus discriminant based models. Okay. Now, discriminant based models are even more simple, right? Like in the case of discriminant based models, you don't even have P of ck given x. You directly estimate f of x, right? So it's y. So discriminative is P of y given x. Discriminant is P of, sorry, not P. It's just f of x, right? Now, if you remember our very first discussion about classification, in classification usually there are 2 stages, right? So first there's inference, then you have decision. The inference is this idea of computing P of y given x, and decision is this idea of using P of y given x and the loss matrix to compute the optimal decision, right? In some sense, discriminant based models just compress all together. Like there's no separate decision stage. Like you just directly try to estimate the function. Okay. Now, this is useful in some situations, but there are some situations where discriminant-based models are not useful, okay? So now there are many, many advantages in having access to P of Ck given X, okay? So let's talk about advantages of P of Ck given X, okay? So the first advantage is minimizing risk, okay? Now, let's say that the loss matrix is not simple 0-1 matrix. You might be working in a financial application, like, or a medical application, where the loss matrix changes. It could be either seasonal change or it could be daily change, okay? If your loss matrix changes once in a while, then with discriminative models, it doesn't affect the model at all, because the model is only estimating P of Y given X, right? There are two components in decision, P of Y given X and the loss matrix, right? So loss matrix changing doesn't have any effect in P of Y given X. So I don't need to retrain my model. I can use the same model. Every day you give me a new loss matrix, I'll tell you what is the correct class based on the loss matrix. However, if you do discriminant-based models, then there is no way to separate P of Y given X and loss matrix. So every day somebody tells, oh, you have to change the loss matrix, you have to retrain your entire system again. Okay, so this is one place where you can minimize the risk. By risk, we just mean like the loss, okay? So you can minimize the risk easily, like continuously, by using P of Y given X, okay? Now the second place where P of Y given X is very useful is situations where you have data imbalance. Okay, now I think several of you gave examples about cancer or fraud detection, right? Like, so these are example problems where you are going to have 99% no cancer or no fraud, and just 1% of the data being cancer or fraud, right? Like, so now you have such a high imbalance, right? Now, when you have data imbalance, it is very difficult to solve. Like, most of these methods will not work. Okay, so it is very difficult to get good solutions. Okay, now why? Because, for example, let's take cancer. An algorithm which says there is no cancer all the time is going to have 99% accuracy. Is that a good algorithm? No, right? So it's a bad algorithm because our goal is to capture that 1%, right? So now, how do I solve this issue? So one way to solve this issue is by first balancing your data set. Okay, so the solution is like this. Like, first you sample the rare class more and balance the distribution of the data set. Okay, if you have 1% and 99%, you sample this 1% class more so that you have 50-50 data. Okay, now you learn the posterior probabilities. Learn the posterior probabilities. P of Ck given X, okay? However, there is an issue here. The issue is my initial prior probability was 1 versus 99, right? I artificially made it 50-50 and I computed this posterior. So I should first correct this 50-50 balancing that I did so that my posteriors are more accurate, right? Now it is actually very, very simple if you have access to P of Y given X, because the new posterior is given by the old posterior, okay, divided by class fraction of sample data multiplied by class fraction in original data. Is that clear? I can just play with the fractions and I will get an estimate as if I started with the original probability distribution. Is that clear? Yeah?
It's old posterior divided by what?
Okay, so the old posterior is the posterior distribution I computed from the balanced data set. Okay. However, I am looking for a classification algorithm, like classifier for the imbalance data set, right? So I can retrieve it by just adjusting the probabilities. Like so, I take the old posterior, I divide it by the class fraction. I'm just changing the denominator. Like instead of using the new 50-50 probability, I'm going back to the original 1:99 probability. Is that clear?
Is it because only periods are changing here, right?
Yes. Yes.
Peaks giving class.
It decomposes. Yeah. Yeah, that's a good point. Okay. Well, I know I should stop, but I'm going to take a couple of minutes to finish this topic. Okay. So there are a few more reasons why P of y given x is important. Okay. The third reason is if you have access to P of y given x, then you can actually combine many models much more easily. Okay, so combining models. How? Let us say there are two important medical tests that somebody has to do to identify the disease. Okay. Now in this case, I'm interested in P of CK given x1, x2. Okay. Now we know that this is proportional to P of x1, x2 given CK, P of CK. Right? Now, if I make naive Bayes assumption, this becomes P of x1 given CK, P of x2 given CK, P of CK. Right? If I have a separate classifier for the first test and a separate classifier for the second test, okay, then I can just estimate the posterior probabilities there and just plug in it here. So it becomes P of CK given x1, P of CK given x2 multiplied by P of CK. Okay, it's very simple. Like so, we can combine two classifiers. We can combine this classifier and this classifier to construct this new classifier, as if we conditioned on both x1 and x2. Is that clear? And finally, we can use P of y given x for reject option, which means I will compute P of CK given x for all the classes. Okay. Now, if I see that all the classes have very low probability, then probably my classifier is not confident about this prediction problem. I can just tell the user, hey, I cannot make this classification. Okay, I'll give you an example. Let's say we have a two-class problem. If my classifier says its probability is close to 0.5, 0.5, then my classifier is probably not confident about the class. So it's better I don't make this decision now, right? Similarly, if you have a four-class problem, if your classifier says 0.25, 0.25, 0.25, okay, but this is a fake number, like it's not going to be exactly 0.25, something close to 0.25 also, right? So then it basically means that my classifier is not confident about one particular class. Like on the other hand, like if I have something like 0.8, 0.1, 0.5, 0.5, 0.05. If I have a probability like this, then I can say that, oh, my classifier is very confident that P of y given, like the class should be class 1, right? Like so you can actually use this prior probability, like posterior probabilities to like basically decide whether to even make the classification or not. Okay, so okay, I think we will stop here and take a 10-minute break. So we will continue at 2:50.